Okay, so this is notes for AP Chemistry, pages 94 and 95. This is the last lesson of Electrochem. Last time, we looked at how to find voltage at standard conditions. And again, standard conditions is 1 molarity for anything in solution, 1 atmosphere for any gas, and usually 25 degrees Celsius, but don't have to be that. So of course, the obvious question that comes up now is what if you aren't at standard conditions? Because unless you set things to be exactly there, you're not likely going to be there. And even if you do start there, things start changing once the reaction happens. Your concentrations and your pressures start changing, and probably your temperature too. So we did this way back in thermo. We solved for delta G naught standard, and then we solved for delta G not. Well, we're doing the same thing now. So we're doing the not, otherwise known as not at standard conditions. So to do this, there's a new equation called the Nernst equation. And it's kind of a large, a little bit scary looking, but some of it we can combine so it's not so much of a mess. So E naught is our voltage at standard conditions. E is our voltage at any condition. Then we have a bunch of constants. R is the usual R, but it's the same one from thermo. You'll see it here, 8.314 joules per mole Kelvin. T is temperature, which if we assume 25 degrees Celsius, we can say that's a constant. F's the Faraday constant, which we've been using to convert between coulombs and a mole of electrons, but it also has a different unit that I have right here, joules per mole volt. And this is going to be more useful in this equation, same number though. N is the number of electrons that is being transferred, the number of moles of electrons that's being transferred. And then we have natural log, and then Q is the reaction quotient, which we've seen before. It's the same thing as an equilibrium constant, but not necessarily at equilibrium. Now, you can use this equation and you can plug in R and T and F every time, but we will almost always do it at 25 degrees Celsius. So I can take R, T, and F, plug in their values, R, T, and F, and just solve for it once, and we get 0.0257 volts. Notice the joules cancels, the moles cancels, the Kelvin cancels, and you end up with volts in the denominator of the denominator, which then moves up to the normal numerator. And so a modified version of the Nernst equation is right here. And that's going to be a little bit faster. You're welcome to use either one. The only time you have to use the original is if the temperature's changing, you're going to have to go to that one because the 0.0257 will not be correct anymore. Okay, let's jump to the first problem. So, kind of a random reaction. We have oxygen being reduced to water in acid, and we have bromine ions becoming bromine liquid, which would be kind of dangerous. So I don't know if this is really a practical reaction, but it does happen spontaneously. If we split it into the two halves, like I have, and make sure our electrons are matching. Look up the voltages from the reduction potential chart, page 481 in the book, or wherever you choose to look it up. Add up your voltages, and you get that it is, under standard conditions, positive 0.152 volts, which isn't a very high voltage, but it is spontaneous, or thermodynamically favorable if you want to use the fancy term. And what I want to do is change conditions. So this is at standard. And if you look at the problem, our pressure of oxygen is standard. That hasn't changed. But our hydrogen ion and our bromine ion are lower than normal. They're 0.10 molarity, so they're 10 times weaker. So we're going to see what that does. Okay, we already know E naught. I recommend now you solve for the reaction quotient by itself, because that usually can be a bit of work. In this particular reaction, nobody goes on top because water's a liquid and bromine's a liquid. That's kind of weird. And on the bottom, everybody goes there. We got the pressure of oxygen, got our hydrogen ion, our bromine. Plug in the values that were given, and you get a Q of 1 times 10 to the 8th, which is pretty big. Next, plug everything into the Nernst. So here is my E naught. I did this one using all the values. I didn't use the shortcut that I showed you above. I think I did it this way just so you would see it this way. Notice the 4 came from my half equations with the 4 here and the 4 here. Often in some of these problems, you don't need to worry about getting your electrons equal, like some of the recent problems we've done. But in this case, you need to do that because you need to be able to write your Q expression where your electrons being given and taken are equal, even though they don't affect the voltages over here. And then natural log, plug in the Q, go through the math. In this case, I would do the log of this first, then all this mess in the middle, and then subtract that from the 0.152, and you get positive 0.034. So it's still spontaneous, but it's lower. It went from 0.152 volts to 0.034. So it's still spontaneous, but it's not pushing as hard. And that makes sense because the two things that aren't standard are reactants, hydrogen and bromide or bromine ion. Well, it makes sense. If you lower the concentration of a reactant, it might still go forwards. It's just not going to do it with as much aggression. All right, next one. It's a little bit more of a normal problem here. We have zinc being oxidized, silver being reduced. This one ends up having a pretty high voltage. The standard voltage is 1.561, and that's pretty good actually. My note up here has nothing to do with the lesson. This is just a reference to Back to the Future, just because I kept seeing that 1.21. So I couldn't help it. Even though watts is a different thing than volts, I just saw the 1.21. In this case, they're telling us that it was measured to be 1.21 volts and that they're keeping the zinc ion 1 molarity. We want to know what's the silver ion. So notice what they said the voltage was is different than standard. So I plugged in what they said it was here, plugged in E naught here. I'm using the shortcut. Fortunately, this one worked out that it was pretty easy, only 2 electrons. So that's my N of 2. And ultimately, the silver ion is going to be in Q. I recommend we just call it Q for now. And then once we solve for Q, we can deal with that. So you're going to have to do some subtraction over here, and that's going to give you this negative 0.35. You then have to multiply by 2, divide by 0.0257. And at that point, you end up with this spot right here. And at this point, we only have 2 sig figs, and we have to undo a log, which means we lose another sig fig. So now we only have 1 sig fig. That equals Q. In this case, Q is our zinc ion over our silver ion squared. They told us that zinc is 1. Solve for the silver. Don't forget to deal with the square there. And you end up with a 1 times 10 to the negative 6 molarity. It ends up being kind of silly that it only has 1 sig fig, but that's just the way it works out. If a problem ever happens and you end up getting 0 sig figs, just finish the problem and just give the answer a couple sig figs. Sometimes that happens with the math we're dealing with. I don't remember why I made this comment here, because it ends up with a ridiculous answer, 7 times 10 to the 11 molarity. That doesn't make any sense. I'm not sure what I was after there, so don't worry about that. If I remember what it is, I'll go over it. If delta G is less than 0, in other words, if delta G is negative, it means it's spontaneous. And if E is greater than 0, in other words, it's positive. I don't know why I put a 1 there. Get rid of the 1. Then it means that it's spontaneous. So they're both saying the same thing. Or again, the proper term, according to the College Board, is thermodynamically favorable. So you can solve for whether a reaction is going to happen this way or this way, and they should agree. Like if one of them says the reaction is spontaneous and the other one says it isn't, then there's something wrong there. Unless voltage just isn't a part of the situation. Now, it turns out there's a relationship between these two things. No surprise there. Here's the equation. Delta G equals negative NFE. In this particular version, everything's at standard conditions. And be aware, if you were to solve for delta G, this one's in joules. We usually did everything in kilojoules when we did thermo, so be careful. And that goes all the way back to, if you look here in this mess, you'll see that this R and the Faraday constant are in joules. So that's where the joules comes from. All right. For some cell, E naught is 1.20 volts, which is kind of a standard battery. It's often 1.2 volts. Delta G naught, if N is 1, 2, or 3, gotcha. So we're going to use this equation, and we're going to do it 3 different ways. We're going to say N is 1, or 2, or 3. Faraday constant's the same every time. The E naught's the same every time. And you just go through the motions, pretty easy calculation, and you get these 3 answers. Notice they're all negative. So since delta G is negative, the reaction is spontaneous every time. Similarly, the voltage was exactly a positive 1.20 every time, so that also says that it's spontaneous. And what this means in the end is that since the voltage is the same every time, how hard the electricity is being pushed is the same. But if you have more electrons being pushed, you're going to get more energy. So it's just interesting that changing the number of electrons doesn't change the push necessarily, and it doesn't change whether the reaction will happen or not. It just simply says more electrons being pushed will be more energy, which we see in this calculation. And looks like that's about it there. Yeah. And now at this point, we have finished the notes for electrochem.